So let's talk more about exponential growth. Remember, for any new population, whether it's humans or anything else, typically populations, when they move to a new habitat, they start out growing exponentially, and then something else happens. So we're going to start with exponential growth, and we'll spend Wednesday and Thursday talking about what happens after exponential growth ends. And our situation this year leads us to a unique situation where we can actually look at what would happen if the coronavirus, or really the number of people infected with the coronavirus, had grown exponentially. So let's just say that the first person in the US was infected basically in the first week of the year, the first week in January. It seems that with no social distancing, no effort to stop the spread, that this virus spreads from one infected person to two new people. Basically, if one person is infected, that person infects, on average, two new people, and that process takes about a week. Well, how long would it take? Again, this is with no quarantine, no social distancing, no virtual school. How long would it take for everyone in the US to get infected? Or really, how many people would get infected with the virus this year? And this is something that people really don't understand about exponential growth, is that our brains tend to think in a linear way, and linear systems just work very, very differently. And this really explains why it's so necessary for us to be in quarantine, to be social distancing, and to be in virtual school. Because with no efforts to curb this virus, basically what we would find is that everyone would get infected really, really quickly. So let's actually start by looking at the math behind that. And this table looks a little complicated, but I'll take some time and I'll walk you through it. So again, the situation here is in the first week of the year, we have one newly infected patient in the US. That one infected person, over the course of 1 week, infects two new people. Those two people each then infect two more people each. So that's a total of 4 people, and so on for the year. And again, we're looking at how long it takes to infect everyone and how many people would be infected by the end of the year. So there are mathematical formulas that tell us basically how many new infections there are and then what the total number of infections are. So if we look at week 1, so week 1 we have one infected person. Well, 1 is equal to 2 raised to the power of 0. So 2, or really any number raised to the power of 0 is 1. To find the total number of infections in the US for week 1, what we do is we raise 2 to the power of 1. That's the week that we're in, week 1. 2 to the 1 is 2, and then we subtract 1 from that number. So 2 to the 1 is 2, minus 1 is 1. We have a total of 1 infected person in the whole country. Over the course of the next week, that one person infects 2 new people. So we have 2 new infections. The number of new infections is 2 to the 1. And then the total number of infections is 3. The 2 that are new this week plus the 1 new one from last week. Well, the total number of infections is 2 raised to the power of 2, or 2 squared, which is 4, minus 1. We have 3 total infections. The next week, each of those 2 newly infected people infect 2 more people. So we have 4 new infections. 4 is equal to 2 squared, and then for the total number of infections, it's the 3 from the previous week, plus the 4 new ones for this week. So it's a total of 7 people infected in the third week. The last week in January, so we're at the end of the first month, we have 8 new infections and 15 total people infected. And remember, there was a point where President Trump came on TV and he said, oh, we're at 15 people infected, and I expect that to get close to zero quickly. Well, 15 people infected is actually kind of a lot for a system that is growing exponentially, for a population that's growing exponentially. It may not seem that much, to have 15 people infected at the end of January, but the infection grows exponentially, not linearly, and that's something that unfortunately not enough people understand. Because to figure out how many infected people you have, either newly infected or total infection, sort of cumulative for the entire year, what you need to know is basically how much time has passed, how many weeks have passed, because this virus seems to double in population every week or so. Well, the formula for the number of new infections is you raise 2 to the power of whatever week it is, whether it's week 4, 3, 2, 1, 20, 29, 50, whatever week we're in. If you want to know how many new people are going to get infected that week, you take 2 and you raise it to the power of the week that you're in minus 1. So in week n, we're taking 2 to the power of n minus 1. In week 4, we're taking 2 to the power of 4 minus 1, which is 3. In week 3, 2 to the power of 3 minus 1, which is 2. To find the total number of infected people, what you need to do is take whatever week you're in, you raise 2 to that power, and then just subtract 1 from the total number after raising 2 to that power. So what it turns out is that if we had done absolutely nothing to stop the spread of this virus, no social distancing, no quarantine, no virtual school, every single person in America would likely have been infected by the 29th week of the year. Well, when does the 29th week of the year fall? It's sometime in mid to late July. So basically, the middle of summer, what we would have is about 270 million new cases of coronavirus in that week alone. There are only about 350 million people in the US. At that point, after that week, the total number of cases would be 500 and almost 37 million. Again, that's more people than are in the entire US. So at some point in mid-July, everyone would have caught this virus. It seems to have a fatality rate of about 6%. So it would have killed off about 6% of the US by the time August rolls around if we just did nothing. So that's one of the reasons why it's so important for us to be in virtual school, for us to be socially distancing, to be in quarantine, and to really take steps to slow the spread of this virus so that it's not doubling every week. Because if it did, we all would have caught it, and 6 out of every 100 of us would have died from it. Actually, that number could have been higher potentially, because hospitals would have become so overwhelmed that they couldn't treat every infected person as well as they are treating them now, with the rate at which it's spreading being much lower. And just to show what would happen if we just let the virus continue to spread somehow for the entire year, there are 52 weeks in a year. In that 52nd week, the number of new cases would be, this is 2.2 quadrillion new cases, which is far, far more people than have ever lived in the history of the planet. The total number of cases would be almost twice that. Again, way more people than have ever lived on Earth since the beginning of time. It's just an absurd number of people. So without us taking all of the measures that we did take, basically this virus would have infected everyone very quickly, this calendar year, which again, you wouldn't really expect with only 15 people infected at the end of January. It's really sort of counterintuitive. It messes with our brain to think that, okay, at the end of January, we have 15 people infected, but by August, we all would have caught it. That it doesn't really jive with how our brains work. Our brains work in a linear fashion, and populations just don't grow linearly. They don't. Whether we're talking about people who are infected or just human populations in general. And that's why it's so important for us to understand exponential growth, because it's not something that is instinctual for us. It goes against sort of our sense of the everyday. Um, and we have to really sort of pause and take a moment to understand the math, which is basically never fun, but in this case, it's extremely important. So if we look at any population, whether we're looking at the population of people infected with coronavirus or just a population of people and how fast it's growing, we can look at something called the doubling time. Like I mentioned, for coronavirus, if we take no measures at all, the doubling time seems to be about 1 week. Uh, Basically, the doubling time is the amount of time it takes for that population to double in size. For any human population, if you look at the global human population throughout history or any particular country today, the doubling time is usually several decades long. And it's something that is relatively easy to calculate if you know the annual percent growth rate for a population. To calculate the annual percent growth rate, or APG, you need the birth rate and the death rate. And most human populations, again, whether we're looking at globally or individual countries, have an APG somewhere between 0% and 2%. 2% is fairly high. Like I mentioned yesterday, there are some countries that actually have a negative um, that have negative population growth rates, but most human populations are somewhere between 0 and 2. So the formula for the annual percent growth rate is the birth rate in births per 1,000 individuals minus the death rate in deaths per 1,000 individuals, and then you have to put that in parentheses. If you don't, when you're plugging these numbers into your calculator, what your calculator will do is take the death rate and divide it by 10, and then subtract that number from the birth rate. So it's birth rate minus death rate in parentheses, and then that number divided by 10. And then the doubling time. There is a more accurate formula for doubling time, but it involves math that you probably haven't done. Uh, so there's a much simpler formula that gives us a reasonable approximation of what the doubling time is from the APG. And that formula is just that the doubling time equals 70 divided by the APG. If the APG is 1, then the doubling time is 70. If the APG is 2, the doubling time is 35. If the doubling time is 0, or if the APG is 0, then the doubling time is infinite. If the population isn't growing, it will take forever to double. That kind of makes sense. So the higher the APG, the faster the population is growing, the shorter the doubling time. The lower the APG, the higher the doubling time. An annual percent growth rate above 1 will give us a doubling time less than 70. An annual percent growth rate below 1 will give us a doubling time of more than 70. So I know you don't always like to talk about biology and population, so I thought I would use an example where we look at money. So, you're in high school right now, you're, let's say, about 16 years old, you turn 16 at some point this summer or within the next year, and you work the summer and you earn $1,000. And instead of spending it on whatever you kids spend your money on these days, like a single new phone, you invest that money. You invest it in the stock market, just in some broad general stocks that are representative of what the stock market does. Historically, if you look, over decades, the stock market, the money invested in the stock market tends to grow about 10% per year on average, has an APG of 10. Now, yes, there are recessions and depressions that drive that number down, but there are also booms that drive that market up. So for let's say a period from when you're 16 until you're 65, period of 49 years, basically your working lifetime, it should be about 10% per year. So you're 16 now, you invest $1,000 this summer when you're 16. How much money will you have when you're 65 and you're ready to retire? Well, let's look at the APG, let's look at the doubling time, and see where that takes us. So you start out with $1,000 invested. Well, the doubling time is 70 divided by the APG. If the stock market grows on average at 10% per year, then your money will double every 7 years. You're 16 right now. We're looking 49 years into the future until you're 65. So how many times will your money double? Well, that's just the amount of total time that we're talking about, 49 years, divided by the number of years it takes for your money to double, which is 7. And that gives us 7 as well. What that means is your money will double 7 times from now when you're 16 until the future when you're 65. So how much will your $1,000 that you invest this summer actually be worth when you retire if it grows at 10% per year? Well, after the first doubling time, your $1,000 will have doubled into $2,000. So by the time you turn 23, you will have made $1,000. The second doubling time, that 2,000 will grow into 4,000. After 3 doubling times, you'll have 8,000. 4, you'll have 16. After 5, which is 35 years from now, you'll have 32,000. After 6 doubling times, you'll have 64,000. And after 7 doubling times, that $1,000 that you invested when you were 16 will be worth $128,000. Now remember, this is a one-time investment of $1,000. You never put any more money into this account. You just invest $1,000 this summer and never touch that money again. It's worth $128,000 when you retire. So you could invest $1,000 every year for the next several years, and basically what you would have from when you're 65, you'd have money that would be worth $128,000 for that year. And then the next year, you'd have another $128,000. So you can see how investing, especially early, really makes you a lot of money later. Because let's say that you're not 16 when you invest this money, you wait until you get out of college. Well, let's say 7 years from now, that's one less doubling time, which means you'll have only half as much money. If you wait until you are my age, your money won't even double 5 times. We could both invest $1,000 this year. By the time I retire, I'll only have $16,000. By the time you retire, you'll have $128,000. So investing money, even if it's not that much, which I know $1,000 sounds like a lot, but trust me, when you're an adult, $1,000 goes pretty quick. Investing money when you're young makes a huge, huge difference when you're older. Because of the program that you're in, it's very possible that you'll get a very good paying job basically right out of high school. Some of the graduates from ALPS are making $40,000 or $50,000 a year within a year or two of leaving high school. I would highly recommend that they and you, if you end up in that situation, invest as much of that money as you can, because it will grow exponentially. So back to biology. I want to go through an example of problem like the ones that you have to do today, where we look at the population of people in the Bahamas. So the Bahamas, as a country, the birth rate is 14.8 births per 1,000 people, and the death rate is 7.4 deaths per 1,000 people. What that gives us, when we subtract the death rate from the birth rate and then divide that number by 10, is that the Bahamas has an APG of 0.74. and that's 0.74%. We don't need to do any conversions to that number. We just plug that in to our equation for doubling time, which is 70 divided by the APG, and that gives us 70 divided by 0.74, which gives us a doubling time of about 95 years. So every 95 years, the population of the Bahamas will double. If the population of the Bahamas is about 300,000 today, which it is, it's a little bit more than that, how long will it take for the population of the Bahamas to reach 5 million people? One doubling time is about 95 years. So in 95 years from today, the population of the Bahamas will double from 300,000 to 600,000. How many doubling times will it take to get to 5 million? Well, we can look and just sort of do the math one doubling at a time. We double once from 300 to 600,000, double again from 600,000 to 1.2 million, another doubling from 1.2 million to 2.4 million, and then a fourth doubling brings us from 2.4 million to 4.8 million, which is just about 5 million people. That's 4 doublings. Each doubling takes 95 years, so we multiply 95 times 4, and it'll take 380 plus a few extra years, maybe let's call it 400 years or so, for the population of the Bahamas to go from 300,000 to 5 million. The Bahamas, their population is growing pretty slowly. The global human population has an APG of about 1, a little bit higher than the 0.74 of the Bahamas. So today's assignment, you have some more problems where you calculate APG, and then you use that to calculate doubling time, and we look at some different countries and we see what will happen to those countries in the future, assuming that their APG doesn't change. So this is a couple of practice problems for you to see how to do the ones in the assignment, plus some context with the coronavirus and with investing money in the stock market. And I hope that you learn something both about the coronavirus and about investing and about biology from this assignment.